Take a moment. The light softly touching the wall of your room right now is only a few seconds old, but the stars you see in the sky, their light is millions, sometimes billions of years old. That means when you look up, you are not seeing the present. You are looking into the past. And even now, at this very moment, the universe is expanding faster than before. Galaxies are drifting farther and farther apart. Some stars, whose light is just reaching your eyes, no longer even exist. They faded long ago, yet their final glow is still traveling toward us. Far away, forces are at work that can bend space, slow time, and quietly challenge the limits of our understanding. We do not know everything. Perhaps we know very little, and that is what makes this journey beautiful. Tonight, we will drift among mysteries so vast that the mind slowly begins to grow calm. So take a deeper breath, let the day fall gently behind you, and let's move toward that universe that has always been above us, yet never fully understood. If you enjoy these quiet explorations, you're welcome to like this video, subscribe for more peaceful journeys through science and space, and share a thought in the comments below. For now, just relax. Let the night settle gently around you. Allow your breathing to soften as we drift outward, beyond the quiet glow of familiar stars. The universe often appears calm, almost motionless, as though suspended in perfect stillness. Yet beneath that tranquil surface, something remarkable is unfolding. The universe is expanding. For much of modern science, it was assumed that this expansion, which began long ago, would gradually slow. Gravity, after all, is patient and persistent. It gathers gas into stars, stars into galaxies, and galaxies into immense clusters. Given enough time, gravity seemed destined to ease the outward motion of everything. But careful observations changed that expectation. When astronomers studied distant stellar explosions, brilliant supernovae shining from billions of light years away, they noticed something subtle but profound. Those distant galaxies were farther than predicted. Their light had traveled longer paths than expected. The conclusion was astonishing. The expansion of the universe is not slowing. It is accelerating. Space itself is stretching more quickly over time, gently increasing the distance between galaxies. This is not like objects flying through emptiness. Rather, the emptiness itself is widening. If you imagine dots on the surface of a slowly inflating sphere, each dot moves away from the others as the surface grows. No dot sits at the center. Every point witnesses the same quiet separation. The force behind this acceleration remains unknown. Scientists call it dark energy. The name does not describe what it is, only what it is not. It is not light. It is not ordinary matter. It does not gather into stars or clouds. It appears to be a subtle property woven into space itself, influencing the universe on its largest scales. Some theories suggest it may be constant, an unchanging feature of the cosmic fabric. Others propose it could evolve slowly with time. There are even ideas that our understanding of gravity might shift when distances become unimaginably vast. The implications are profound. If this acceleration continues, galaxies beyond our local cosmic neighborhood would gradually fade from view. Over unimaginable ages, the night sky would grow darker and more solitary. Future observers, living trillions of years from now, might see far fewer galaxies than we do today. And yet, here we are, in a brief era when the cosmos is still richly visible, a moment when distant structures can still be studied, mapped, and quietly admired. The mystery of dark energy does not shout, it whispers. It shapes the destiny of everything while remaining almost invisible to direct detection. As we continue drifting through this vast expansion, we will move toward another quiet question, one that listens rather than stretches. For now, breathe slowly. The universe is growing larger, and we are gently carried within it. As the universe continues its quiet expansion, there is another kind of silence we have learned to pay attention to. It is not the silence of emptiness, but the silence of listening. For decades, scientists have turned their instruments toward the sky, not to look, but to hear. The night above us appears serene, yet it may carry signals we have not yet recognized. Radio waves drift across space from natural sources, spinning stars, collapsing remnants, distant galaxies. Amid this steady cosmic background, researchers search for something unusual, a pattern too precise to be random, a signal too narrow to be natural, a repetition that suggests intention rather than accident. If such a signal were ever detected, it would not be announced immediately. First would come caution. Instruments would be checked for error. Satellites, aircraft, and ground transmitters would be ruled out. Other observatories in distant parts of the world would be asked to confirm the same whisper from the same point in the sky. Only after careful verification would the possibility be considered. What might such a signal look like? It would likely be concentrated in a narrow range of frequencies, standing out from the broader noise of the universe. It might repeat with deliberate rhythm. It might remain fixed against the slow rotation of the stars, suggesting a source far beyond Earth. And yet, even then, interpretation would be slow. A signal does not automatically reveal its meaning. It could be a deliberate beacon sent outward like a lighthouse across cosmic distances. Or it might be unintentional leakage from technology, radiating into space without purpose of contact. The idea of a confirmed extraterrestrial signal is profound, not because of drama, but because of implication. It would quietly answer one of humanity's oldest questions. We would know that the ability to shape matter into transmitters and receivers, to wonder and to communicate, is not unique to this small planet. Until that day, the listening continues. Large radio dishes sweep across the sky. Arrays of antennas combine their signals to sharpen resolution. Computers sift through immense volumes of data, searching for patterns that do not fit known astrophysical processes. Most anomalies fade under scrutiny, revealed as interference or misunderstood natural events, but the search persists. There is something deeply peaceful about this effort. It is patient, it is methodical, it accepts long stretches of quiet. It recognizes that the universe does not rush to answer. Perhaps the most remarkable aspect is this: the sky has been transmitting for billions of years. If a message is out there, it has likely been traveling across vast distances, crossing interstellar space at the speed of light. It may already be near us, or it may still be generations away. For now, we remain attentive. The cosmos expands outward, and we listen inward into the silence between the stars. As we continue drifting outward, looking and listening, our telescopes do something remarkable. They allow us to look backward in time. Light does not travel instantly. It moves at a steady, finite speed. So when we observe a galaxy billions of light years away, We are not seeing it as it is now. We are seeing it as it was billions of years ago, when the universe itself was much younger. In recent years, increasingly powerful observatories have revealed galaxies that appear surprisingly mature for their age. These distant systems shine brightly, already structured, already rich with stars, at a time when the cosmos was thought to be in its early stages of assembly. According to many models, galaxies in that era should have been smaller, more chaotic, and still in the process of gradual formation. Yet some observations suggest otherwise. These early galaxies appear massive and organized, containing heavy elements that require generations of stars to create. This raises a gentle but persistent question. Did stars form more rapidly in the early universe than expected? Were the first stars unusually large, burning hot and fast, enriching their surroundings more quickly than our models predict? There are other possibilities. Gas may have cooled efficiently under conditions we are only beginning to understand. Black holes may have formed early, shaping their host galaxies through powerful outflows and gravitational influence. Or perhaps dust and complex star formation processes are affecting how we interpret the light, making young systems appear older than they truly are. Each new observation adds detail. Spectra help confirm distances and chemical composition. Careful measurements refine estimates of mass and age. With every improvement in technology, the picture becomes clearer, yet also more intricate. What makes this mystery soothing rather than unsettling is its openness. Science does not resist revision, it welcomes refinement. When data challenge expectation, theories evolve. The universe is not obligated to match our first assumptions. It unfolds according to its own quiet logic. Looking so far into space is like opening an ancient archive. We are reading the earliest accessible chapters of cosmic history. We see the glow of young stars, the merging of proto-galaxies, the gradual layering of structure, and occasionally we find something that seems ahead of schedule. Perhaps the early universe was more efficient than we imagined. Perhaps conditions allowed rapid growth in ways we are still uncovering. Or perhaps our interpretation will shift again as instruments become even more sensitive. For now, the light continues to arrive. Photons that began their journey billions of years ago finally reach our detectors, carrying information across incomprehensible distances. We sit quietly beneath the sky, receiving messages from epochs long past. The universe expands, galaxies assemble, and the earliest chapters of existence slowly reveal themselves, one faint glimmer at a time. As we travel farther in thought, beyond expanding space and ancient galaxies, another quiet question begins to form. How large is the universe truly? Not just the part we can see, but the whole of it. There is a limit to our vision. Light has traveled for a finite amount of time since the universe began expanding. Because of this, we can observe only a certain region around us, often called the observable universe. Beyond that boundary, light has not yet had enough time to reach us. But the absence of visibility does not imply an edge. Beyond our horizon, space continues. Whether it continues forever is a question that remains open. One possibility is that the universe is infinite, stretching endlessly in all directions. In such a reality, galaxies extend beyond our sight without boundary. There would be no outer wall, no final frontier, only continuous expansion. Another possibility is more subtle. The universe could be finite, yet unbounded. Imagine the surface of a sphere. It has limited area, yet no edge. If you traveled far enough in one direction, you would eventually return to your starting point, not because you reached a wall, but because the surface curves back upon itself. Some cosmological models allow similar shapes in 3 dimensions, far more complex than simple spheres, perhaps with gentle curvature or repeating patterns across immense scales. How would we know? Astronomers search for clues in the oldest light in the universe, the faint cosmic microwave background. This ancient radiation carries imprints from an early era when the universe first became transparent. By mapping subtle temperature variations across the sky, scientists look for repeating patterns or distortions that might hint at overall shape and curvature. So far, observations suggest the universe is remarkably flat on large scales. But flat does not necessarily mean infinite. It simply means that if there is curvature, it is too subtle for current measurements to detect. This uncertainty is not frustrating, it is humbling. The possibility that the cosmos extends far beyond what we will ever observe invites a quiet sense of scale. Our visible region may be only a small patch of something vastly larger. And beyond even that lies another gentle mystery. If the universe is infinite, then patterns of matter may repeat somewhere, unimaginably distant. If it is finite, its shape could be stranger than any simple analogy suggests. For now, we rest within our observable bubble, surrounded by galaxies whose light has reached us in time. Beyond that luminous boundary, the darkness continues, not as emptiness, but as unseen structure awaiting discovery. Space expands, horizons shift, and the full shape of reality remains softly beyond our reach. As we rest within our observable horizon, another question slowly rises from the quiet depths of thought. If the universe is expanding now, and if we can trace that expansion backward in time, what lies at the very beginning? Our current understanding suggests that the universe began in an extremely hot, dense state, not as an explosion into empty space, but as the rapid expansion of space itself. In those earliest moments, energy and matter were intertwined in ways difficult to imagine. Temperatures were so immense that familiar particles could not exist as they do today. We can describe much of what happened after the first tiny fraction of a second. Equations model how matter cooled, how particles formed, how light eventually separated from plasma and began its long journey across the cosmos. But when we push our mathematics closer to the very beginning, our understanding grows uncertain. Gravity, which governs planets and galaxies so reliably, behaves differently at extremely small scales and immense energies. Quantum physics, which describes the microscopic world with astonishing precision, also dominates those early conditions. Yet when we try to combine these two powerful frameworks, our equations lose clarity. They point toward infinities and contradictions. What happened before that earliest describable moment? Some physicists suggest the question itself may not have meaning. If time began with the expansion, then asking what came before may be like asking what lies north of the North Pole. The concept might simply not apply. Others explore more imaginative possibilities. Perhaps the universe experienced a previous phase of contraction, compressing until it reached extreme density, then rebounding in a new expansion. In such models, our cosmos could be part of an ongoing cycle. There are also theories proposing that our universe formed as a kind of bubble within a larger cosmic landscape, one region among many with varying physical properties. Another idea arises from quantum theory itself. At the smallest scales, fluctuations constantly appear and vanish, Some suggest that under certain conditions, such fluctuations could give rise to entire universes, emerging from underlying fields in ways we are only beginning to grasp. The difficulty lies in evidence. The earliest moments left only faint traces. Much of the information from that era may be forever inaccessible, smoothed away by subsequent expansion. We search for subtle signatures in cosmic background radiation, gravitational waves, and particle behavior that might hint at those primal conditions. The origin question remains gentle yet profound. It asks not only how the universe evolved, but what kind of reality allows space and time to emerge at all. As we breathe slowly beneath the stars, we recognize something comforting. Even without complete answers, the investigation continues. Each discovery brings us closer to understanding the deep architecture of existence. The universe expands forward. Its beginning remains softly veiled, and we continue to wonder. As we move gently away from the question of beginnings, we return to our own cosmic neighborhood. Among the planets that circle our star, there is one world that feels both familiar and deeply strange. It is nearly the same size as Earth. It formed from similar materials, and yet its story unfolded along a very different path. Venus. At first glance, Venus might seem like Earth's twin, but its atmosphere is thick and heavy, composed largely of carbon dioxide. Clouds of sulfuric acid drift high above its surface. Beneath them lies a landscape hot enough to melt lead. Pressures at the surface are crushing, far greater than anything we experience here. And then there is its rotation. Most planets spin in the same general direction as they orbit their star. Venus does not. It rotates slowly in the opposite direction of many of its neighbors. A single day on Venus lasts longer than its year. The sun would appear to rise in the west and set in the east. Why? One possibility is a dramatic past. Early in the history of the solar system, collisions were common. Protoplanets and massive fragments moved through chaotic orbits. A sufficiently large impact could have altered Venus's rotation, perhaps even flipping it. Such a collision would not be visible today, but its effects might remain in the planet's unusual spin. Another possibility is quieter but persistent. Venus possesses a dense atmosphere that interacts strongly with sunlight and tidal forces from the sun. Over immense spans of time, these forces may have gradually altered its rotation. The slow gravitational tug of solar tides, combined with atmospheric dynamics, could have reshaped the planet's motion without a single catastrophic event. Venus also exhibits atmospheric superrotation. Its upper winds race around the planet far faster than the surface turns. This complex motion may subtly interact with the planet's interior, contributing to its unusual behavior. The connection between rotation, climate, and atmospheric circulation remains an active area of study. Understanding Venus is more than curiosity. It offers perspective. Two planets, similar in size and composition, evolved into radically different worlds. Earth became temperate and life-supporting. Venus became extreme and hostile. Somewhere along the way, small differences amplified into profound divergence. Rotation influences weather patterns, heat distribution, and magnetic fields. Even subtle changes in spin can alter a planet's destiny over billions of years. Venus reminds us that planetary evolution is delicate. Outcomes are not predetermined. They depend on initial conditions, interactions, and feedback processes that unfold gradually. As we continue drifting through our solar system, we carry this quiet realization. Even worlds that begin alike can end differently. The universe is vast, but sometimes the most intriguing mysteries lie close to home, spinning slowly beneath thick, glowing clouds. From the thick clouds of Venus, we drift outward to another neighboring world, colder and quieter, yet filled with its own subtle intrigue. Mars has long captured human imagination. Its reddish surface, etched with valleys and ancient riverbeds, suggests a past very different from its present. Today, Mars is dry and thinly blanketed by a fragile atmosphere. But evidence indicates that long ago, liquid water flowed across its surface. Rivers carved channels, lakes collected in basins, perhaps even shallow seas once reflected a pale sun. Over time, much of that water vanished, either escaping into space or freezing beneath the ground. Yet Mars still offers surprises. One of its most debated mysteries involves methane. Methane is a simple molecule composed of carbon and hydrogen, but it carries significant implications. On Earth, much of our atmospheric methane is produced by living organisms. Microbes deep underground and in wetlands release it as part of their metabolism. However, methane can also arise through purely geological processes without biology. The curious part is that methane does not remain stable for long in a planet's atmosphere. Sunlight and chemical reactions gradually break it apart. So if methane is detected on Mars, it suggests that something is actively replenishing it. Over the years, various instruments have reported hints of methane in the Martian air. Some observations suggest faint seasonal fluctuations. Others detect localized plumes that appear and fade. Yet not all measurements agree. Certain missions have found little to no methane at all. The signals are subtle, and interpretation is challenging. If methane is present, what could be producing it? One possibility involves chemical reactions between water and certain types of rock beneath the surface. When water interacts with specific minerals, methane can form naturally. Another idea is that ancient methane, trapped in ice or clathrate structures, is occasionally released through cracks in the crust. And then there is the more dramatic possibility. Microbial life, hidden underground, could generate methane as a byproduct. Such organisms would not require sunlight. They could exist in protected niches, sheltered from harsh surface radiation. At present, no definitive conclusion has been reached. The smartest approach is patience. Scientists continue mapping methane concentrations, correlating them with seasons, geology, and atmospheric circulation. Each new data set adds another piece to the puzzle. Mars does not reveal its secrets easily. It offers hints, not declarations. As we glide gently past its dusty plains and frozen poles, we sense that this small world still carries unfinished chapters. Beneath its quiet surface may lie chemistry still active, processes still unfolding. Whether geological or biological, the source of Martian methane remains uncertain. And in that uncertainty, the mystery breathes softly. Leaving Mars behind, we travel farther outward into the colder reaches of the solar system, where sunlight grows faint and time seems to move more slowly. There, beyond the orbit of Saturn, drifts a pale blue world that appears calm and featureless from a distance. Uranus. At first glance, Uranus seems simple. A smooth sphere tinted by methane in its atmosphere, quietly circling the sun. But its posture tells a different story. Unlike most planets, Uranus does not spin upright. It lies on its side, tilted dramatically, with its rotation axis nearly aligned with its orbit. Imagine a globe rolling around the sun rather than spinning like a top. That is Uranus. Because of this extreme tilt, its seasons are unlike any other. Each pole experiences decades of continuous sunlight, followed by decades of darkness. Entire hemispheres lean toward the sun, then slowly away in cycles that last many Earth years. The result is a pattern of seasonal extremes that we are only beginning to understand. How did Uranus end up this way? One leading idea suggests a massive collision early in the solar system's history. During that chaotic era, large protoplanets frequently collided and merged. A sufficiently powerful impact could have knocked Uranus onto its side. The planet would have settled into its current orientation over time, carrying the memory of that ancient encounter. Another possibility involves multiple smaller impacts that gradually altered its tilt. Rather than one dramatic blow, a series of gravitational nudges may have slowly shifted its posture. Some models even explore whether interactions with forming moons or leftover disk material could have contributed to the change. Uranus also possesses an unusual magnetic field. Instead of being neatly aligned with its rotation axis, the magnetic field is offset and tilted. This creates a magnetosphere that behaves in complex ways as the planet rotates and orbits the sun. Charged particles interact with this magnetic environment in patterns that remain under study. Despite its distance, Uranus is not entirely quiet. Subtle atmospheric activity has been observed, including faint storms and shifting cloud features. As it moves through its long seasons, changes in sunlight may drive circulation patterns that are only now becoming visible to modern instruments. The planet reminds us that appearances can be deceiving. Beneath a calm exterior may lie a history shaped by violence and gradual transformation. As we drift past this sideways world, we are reminded that planetary systems are dynamic. Orbits shift, axes tilt, collisions alter destinies. Even in the cold outer darkness, evolution continues. Uranus rolls gently around the sun, carrying the silent story of its ancient past. Beyond the tilted calm of Uranus, farther into the deep blue darkness, orbits another distant giant. Neptune moves slowly through the outer solar system, receiving only a fraction of the sunlight that warms Earth. From afar, it appears serene, a smooth sapphire sphere suspended in blackness. Yet Neptune is anything but still. Despite its great distance from the Sun, it hosts some of the fastest winds in the solar system. Powerful currents race through its upper atmosphere at astonishing speeds, shaping clouds and storms that emerge and fade over time. Among its most intriguing features are immense dark vortices, storms that appear like shadowed ovals against its bright blue face. These dark spots are not holes in the atmosphere. They are swirling systems, regions where air circulates in complex patterns, dredging material upward from deeper layers. When sunlight strikes these regions, chemical interactions and variations in cloud thickness create the illusion of darkness. What makes Neptune's storms mysterious is their unpredictability. Some dark vortices grow to enormous sizes, comparable to or even larger than Earth. They drift across the planet's atmosphere, accompanied by bright companion clouds that form along their edges. These clouds are thought to be composed of methane ice crystals lifted high by rising currents near the storm boundaries. And then, after a few years, sometimes even sooner, the storms fade. Unlike Jupiter's long-lived tempests, Neptune's dark spots appear and disappear within relatively short timescales. Observations over decades have shown that new vortices can form unexpectedly, while older ones gradually dissolve into surrounding winds. Why does Neptune remain so dynamic despite receiving so little solar energy? One explanation is that it radiates more internal heat than it absorbs from the sun. This internal warmth may drive convection, fueling powerful atmospheric motion. The planet's deep interior could be slowly releasing energy left over from its formation, sustaining its restless weather. Another factor may involve the structure of its atmosphere and the behavior of its jet streams. The interactions between rising and descending air, combined with rapid rotation, create conditions where vortices can form, migrate, and dissipate. Modern telescopes continue to monitor Neptune, capturing subtle changes in cloud patterns and storm activity. Each new observation provides insight into the mechanics of a distant, frigid world that refuses to remain static. As we drift past Neptune, we recognize a pattern that echoes across the solar system. Even in cold and distant regions, complexity thrives. Energy moves, structures form and fade. The universe is not silent. It breathes through storms and shifting winds, even at the far edges of sunlight. And Neptune, deep in the blue twilight, carries its swirling secrets onward through the dark. From the shifting storms of Neptune, we turn inward once more, toward a world that has long captured human attention. Jupiter, the largest planet in our solar system, dominates its surroundings with immense gravity and swirling bands of color. Among its many features, one stands out as both familiar and mysterious: the Great Red Spot. This vast storm has been observed for centuries. Early astronomers sketched it through modest telescopes, noting a persistent oval embedded within Jupiter's layered clouds. Over time, spacecraft and advanced imaging revealed its scale. At its largest, the Great Red Spot was wide enough to swallow multiple Earths side by side. It is an anticyclone, a high-pressure system rotating counterclockwise in Jupiter's southern hemisphere. Unlike storms on Earth, which draw energy from warm oceans and fade within days or weeks, Jupiter's atmosphere is composed primarily of hydrogen and helium. There is no solid surface beneath the storm, only deeper layers of gas. For generations, the Great Red Spot appeared remarkably stable, but recent measurements show it's slowly shrinking. Though still enormous, its diameter has decreased over the past century. Its color also changes, shifting from deep brick red to softer shades of salmon. What causes its persistence, and what drives its gradual change? Jupiter rotates rapidly, completing a full spin in just under 10 hours. This swift rotation organizes its atmosphere into powerful jet streams that circle the planet in alternating directions. The Great Red Spot sits between these bands, drawing energy from their shear and motion. Smaller vortices occasionally collide with it, merging and contributing momentum. Its distinctive color likely arises from complex chemistry. Material rising from deeper layers may interact with sunlight, producing compounds that tint the upper clouds. Variations in altitude, temperature, and composition influence the hue over time. Scientists study the storm's vertical structure to understand how deep it extends. Does it penetrate far into the planet's interior, or is it relatively shallow compared to Jupiter's vast depth? Data from spacecraft suggest the storm reaches hundreds of kilometers downward, though the full extent remains under investigation.
Will the great red spot eventually disappear, or will it stabilize at a smaller size, persisting for centuries more? For now, it continues to spin, a colossal whirlpool embedded in a planet of perpetual motion. Watching its slow evolution reminds us that even seemingly eternal features can change. The cosmos is dynamic, even on timescales longer than a human lifetime. As we drift away from Jupiter's striped atmosphere, we carry with us the image of that enduring storm, vast, shifting, and still alive after centuries of observation. In the quiet of space, even giants evolve, and the great red spot turns gently onward beneath distant sunlight.
As Jupiter's immense presence fades behind us, we begin to notice something quieter, yet perhaps even more intriguing. Not all mysteries in our solar system revolve around giant planets. Some of the most compelling questions lie hidden within small, icy moons that circle them in patient silence. Far from the warmth of the sun, several moons are locked in delicate gravitational dances with their parent planets. These interactions create subtle forces that stretch and compress their interiors. This process is known as tidal heating. Imagine gently bending a metal paperclip back and forth. With each motion, it warms slightly at the crease. Something similar happens inside certain moons. As they move through slightly elliptical orbits, gravity pulls on them unevenly. When they are closer to their planet, the pull strengthens. When farther away, it eases. This constant flexing generates internal heat. That heat can be enough to keep water liquid beneath thick shells of ice. One of the most compelling possibilities is that hidden oceans may exist beneath frozen surfaces. These oceans would not depend on sunlight. Instead, they would be warmed from within, insulated by layers of ice above. In such environments, chemical reactions between water and rock could create energy gradients, perhaps similar to those that support life in Earth's deep ocean vents. Scientists search for signs of these concealed seas. Surface fractures and ridges may hint at movement beneath. Subtle magnetic measurements can reveal the presence of conductive salty water below the ice. In some cases, plumes of material have been observed erupting into space, offering glimpses of subsurface composition. The idea reshapes our understanding of habitability. Traditionally, life was thought to require proximity to a star within a narrow region where liquid water could exist on a planet's surface. But tidal heating expands that possibility. A small moon orbiting far from sunlight might still host a warm ocean hidden in darkness. These hidden worlds are not visible from afar. They appear as simple points of light through telescopes, yet beneath their icy crusts may lie dynamic environments, circulating water, and complex chemistry. The beauty of this mystery lies in its subtlety. There are no dramatic surface oceans glistening under bright skies. Instead, there are quiet interiors warmed by gravity, shielded from cosmic radiation. As we drift gently beyond Jupiter and its moons, we recognize that the solar system is not merely a collection of frozen rocks and giant gases. It is a layered system of interactions where even small bodies may conceal profound secrets. Beneath ice and stone, heat moves. Oceans may flow in darkness, and in places untouched by sunlight, possibility quietly endures. Beyond the realm of moons warmed by tidal flexing, there exists another possibility, worlds that travel alone. Not every planet remains bound to a star. In the early chaos of planetary formation, gravitational encounters can be violent and unpredictable. Young systems are crowded, massive bodies shift and tug at one another. Occasionally, a planet may be flung outward, escaping its home entirely. Such a world becomes a rogue planet. Drifting through interstellar space, a rogue planet has no sun to orbit, no regular sunrise or sunset. It wanders between the stars, illuminated only faintly by distant starlight. At first thought, such a planet seems cold and lifeless, frozen in perpetual night. Yet even here, mysteries linger. Planets generate internal heat. Some of this warmth comes from radioactive decay within their cores. Some remains from the energy of their formation, slowly leaking outward over billions of years. If a rogue planet were large enough, this internal heat might persist long after it left its star. Beneath a thick atmosphere, that heat could be trapped. Surface temperatures might remain higher than expected. In some scenarios, subsurface oceans could exist even without sunlight, insulated by ice and warmed from within. Darkness does not always mean inactivity. Detecting rogue planets is challenging. They emit little visible light. Instead, astronomers rely on a technique called gravitational microlensing. When a rogue planet passes precisely in front of a distant star, its gravity briefly magnifies the star's light. For a short time, the background star appears brighter. From this subtle brightening, scientists infer the presence and mass of the unseen object. Such events are rare and fleeting, but they have revealed hints of planetary mass objects wandering freely through the galaxy. Some may be as massive as Jupiter, others may be smaller, perhaps even Earth-sized. The thought of countless dark worlds drifting silently between the stars is both haunting and peaceful. These planets move without a fixed home, yet they remain part of the galaxy's vast architecture. They are shaped by the same physics that governs all matter. In the quiet between stars, gravity still guides motion. Internal heat still flows outward. Chemical processes may continue beneath frozen surfaces. As we imagine these solitary travelers, we expand our understanding of what a planet can be. Not all worlds are bathed in sunlight. Some journey alone, sustained by internal warmth and the gentle persistence of natural law. The universe does not confine its creativity to bright, familiar systems. Even in darkness, structure remains. And in the silent spaces between stars, wandering worlds drift onward. As we leave behind the wandering darkness of rogue planets, we turn our attention to something even subtler, something woven into the very structure of reality itself. The universe, as far as we can measure, depends on a delicate balance of fundamental numbers. These numbers are not chosen, they are observed. The strength of gravity, the charge of the electron, the masses of elementary particles, the way nuclear forces bind protons and neutrons together. Each constant shapes the behavior of matter. Each value influences how stars shine, how atoms assemble, how chemistry unfolds. If gravity were slightly stronger, stars might burn hotter and live shorter lives. If it were slightly weaker, matter might struggle to clump together at all. If the electromagnetic force varied, atomic structures could shift dramatically, altering the possibilities for molecules. One particularly striking example involves carbon. In stars, carbon forms through a precise sequence of nuclear reactions. Helium nuclei fuse together in a narrow energy window that allows carbon to exist in stable quantities. If that energy level were different by even a small amount, carbon might be rare. And without carbon, complex chemistry, at least as we know it, would be profoundly altered. Other balances are equally significant. The ratio between matter and radiation in the early universe determined how galaxies formed. The slight asymmetry between matter and antimatter allowed atoms to survive at all. Tiny fluctuations in density, present shortly after the universe began expanding, eventually grew into the vast cosmic web we observe today. The remarkable aspect is not simply that these values exist, it is that they fall within ranges that allow complexity. Why? Some scientists suggest there may be deeper underlying laws that fix these constants inevitably. Perhaps what seems delicate is simply the result of hidden principles we have yet to uncover. Others explore the possibility that multiple universes exist, each with different physical parameters. In such a landscape, only certain combinations would permit long-lived structures. We would naturally find ourselves in one of those rare environments. The question remains open. It is both scientific and philosophical, but it is approached with careful reasoning and observation, not speculation alone. As we reflect on these finely balanced numbers, we are reminded that the universe is not arbitrary. Its laws are consistent, measurable, and astonishingly precise. From the fusion inside stars to the chemistry within cells, everything depends on stable relationships among fundamental forces. The cosmos is vast and sometimes violent, yet at its foundation lies extraordinary order. The constants hold, the forces balance, and within that balance, galaxies form, stars ignite, and consciousness arises to wonder about it all. As we consider the delicate balance of physical laws, we move from the vast scale of constants to something far denser, objects where matter is compressed beyond ordinary imagination. When a massive star exhausts its nuclear fuel, gravity begins to win. The outward pressure from fusion weakens, and the star can no longer support its own weight. In a dramatic collapse, its core implodes. If the remaining mass is within a certain range, the result is a neutron star. A neutron star is small by cosmic standards, typically only about 20 kilometers across. Yet within that compact sphere lies more mass than our Sun. The density is almost beyond comprehension. A fragment no larger than a teaspoon would weigh billions of tons under Earth's gravity. Inside such an object, familiar structures break down. Atoms cannot survive the pressure. Electrons are forced into protons, forming neutrons. The matter becomes something entirely different from the materials we know. Near the surface, exotic arrangements of nuclear matter may form, layers and strands shaped by competing forces, sometimes described metaphorically as nuclear pasta. Deeper still, the structure becomes even more extreme. The boundary between crust and core transitions into matter composed largely of neutrons packed tightly together. The pressure is so immense that ordinary distinctions between particles blur. If, somehow, a small amount of neutron star material were transported to Earth, it would not remain stable. Removed from its native pressure, it would expand violently, changing state almost instantly.
the crushing density exists only because gravity confines it. Neutron stars are extraordinary in motion. Many rotate rapidly, spinning dozens or even hundreds of times per second. Some emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like cosmic lighthouses. When aligned with Earth, we observe steady pulses, precise signals marking each rotation. Their magnetic fields are immense, trillions of times stronger than Earth's. These fields shape surrounding space, accelerating particles and influencing nearby matter. Neutron stars represent the boundary between the familiar and the extreme. They are laboratories of physics under conditions impossible to replicate on Earth. By studying them, scientists test theories about nuclear forces, gravity, and the behavior of matter at its limits. As we drift quietly past these dense remnants, we sense the immense power held within compact forms. The universe is not only vast in distance, it is vast in intensity. Within a sphere no larger than a city lies mass greater than a star, matter compressed beyond imagination. And even in such extremes, the laws of physics continue to hold. From the crushing density of neutron stars, we move to a quieter but equally profound imbalance, one that shaped the entire existence of everything we see. In the earliest moments of the universe, energy transformed into particles. Matter and antimatter emerged together, almost as mirror images. For every particle of matter, there should have been a corresponding particle of antimatter. When matter and antimatter meet, they annihilate, converting back into pure energy. If perfect symmetry had prevailed, the early universe would have become a brilliant flash of radiation. Matter and antimatter would have destroyed one another almost completely, leaving behind little more than light. And yet, that is not what happened. Somehow, in the midst of that primordial balance, a tiny excess of matter remained. For roughly every billion pairs of particles that annihilated, one extra particle of matter survived. That minute asymmetry was enough. From that faint imbalance grew galaxies, stars, planets, and eventually life. Why did matter win? Physicists study subtle violations of symmetry in particle interactions. Certain processes observed in high-energy experiments treat matter and antimatter slightly differently. These effects are small, but they suggest that the laws of physics are not perfectly symmetrical. Over time, in the extreme conditions of the early universe, such differences could have tipped the scales. Yet the asymmetry we measure in laboratories does not fully account for the abundance of matter we observe today. There may be additional processes we have not yet discovered. Perhaps heavy particles, present only briefly in the earliest fractions of a second, decayed in ways that favored matter. Perhaps unknown interactions shaped the outcome. The search continues in particle accelerators and deep underground detectors. Scientists analyze rare decays and track fleeting signals, looking for tiny deviations from perfect balance. Each measurement refines our understanding of how the universe evolved from uniform energy into structured matter. The beauty of this mystery lies in its scale. A difference so small it is almost imperceptible became the foundation of everything tangible. Without it, there would be no atoms, no stars, no breath. As we drift through this realization, we sense how finely tuned existence appears, not by design necessarily, but by outcome. A slight leaning in one direction allowed complexity to unfold. The universe began in near symmetry. A whisper of imbalance changed everything. And from that quiet deviation, the material cosmos emerged, stable enough for stars to shine and for us to wonder beneath their light.
From the quiet imbalance that allowed matter to remain, we turn to particles that rarely stay. They pass through space and through us almost without interaction. They are among the most abundant particles in the universe, yet they are extraordinarily difficult to detect. Neutrinos. Every second, trillions of neutrinos stream through your body. They come from the sun, produced during nuclear fusion in its core. They come from distant cosmic events, exploding stars, colliding remnants, energetic galaxies. They travel nearly at the speed of light, carrying information from places ordinary light cannot escape easily. What makes neutrinos so elusive is their reluctance to interact. They have no electric charge and only tiny mass. They pass through atoms as though they were mostly empty space, which, in fact, they are. A neutrino could cross an entire planet without ever colliding with a single particle. To detect them, scientists build enormous instruments in quiet, shielded environments. Some detectors are buried deep underground, protected by layers of rock that block other forms of radiation. Others are embedded in Antarctic ice or submerged in deep water. These vast volumes serve as targets, waiting for the rare moment when a neutrino does interact. When such an interaction occurs, it can produce a faint flash of light. A subtle blue glow spreads briefly through the medium. Sensitive sensors capture this whisper, allowing researchers to trace the neutrino's energy and direction. Why go to such effort? Because neutrinos carry unique information. Light can be absorbed or scattered. Charged particles are deflected by magnetic fields, but neutrinos travel almost undisturbed from their source. They provide direct insight into the core of the sun, the heart of supernovae, and other extreme environments. Neutrinos also revealed something unexpected about themselves. They can change flavor as they travel. There are three types: electron, muon, and tau neutrinos, and they oscillate between these states. This discovery showed that neutrinos must have mass even if extremely small. It required revisions to earlier assumptions in particle physics. In recent years, detectors have observed neutrinos with astonishingly high energies. These particles must have originated from powerful cosmic accelerators, perhaps near supermassive black holes or within violent astrophysical jets. Their exact sources are still being investigated. Neutrinos remind us that the universe communicates in many ways, not only through visible light or gravitational pull, but through nearly invisible messengers that pass silently through matter. As we rest beneath the night sky, unaware of their constant passage, neutrinos continue their journeys. Quiet travelers, unseen currents flowing through everything, carrying stories from the deepest, most energetic corners of the cosmos. As neutrinos whisper through the universe, there are some that arrive carrying energies so immense they challenge our understanding. These are not the gentle solar neutrinos produced in ordinary fusion. They are particles accelerated to extremes far beyond anything humanity can generate in laboratories. When detectors capture one of these ultra-high energy neutrinos, scientists pause.
the energy recorded suggests a birthplace of extraordinary violence. To create such a particle, nature must operate an accelerator vastly more powerful than any machine built on Earth. One leading candidate lies at the center of distant galaxies. Many galaxies harbor supermassive black holes, millions or even billions of times more massive than our Sun. When matter falls toward these black holes, it does not simply disappear quietly. It forms swirling disks of superheated gas. Magnetic fields twist and snap. Jets of particles can erupt outward at nearly the speed of light. Within those jets, shock waves and turbulent fields may hurl particles to staggering energies. Collisions between accelerated particles could produce neutrinos that then escape, traveling across millions or billions of light years before reaching Earth. Another possible source is the aftermath of massive stellar explosions. When a star collapses or when compact remnants merge, enormous amounts of energy are released. In such cataclysmic moments, particle cascades can form, sending neutrinos racing outward into interstellar space. There are even more speculative ideas. Some theories suggest that relic particles from the early universe, if they exist, might decay and release neutrinos with extreme energies. These possibilities are harder to test, but they remain part of the broader exploration. Tracking these energetic neutrinos is like triangulating faint echoes in a vast canyon. Scientists compare arrival times, energies, and directions. When possible, they coordinate with telescopes observing light, X-rays, or gamma rays from the same region of the sky. If a neutrino and a burst of light arrive from a similar direction at nearly the same time, the connection becomes stronger. In recent years, a few such associations have been made. A distant active galaxy has been linked to high-energy neutrino detections, offering one of the first direct clues about their origins. Yet many detections remain unassigned, their birthplaces uncertain. These particles remind us that the universe is not only serene. Beneath its calm appearance lies relentless activity. Black holes feed, stars explode, fields twist and accelerate matter to near light speed. And through all of it, neutrinos travel freely, unaffected by magnetic fields or intervening matter, bearing witness to processes too extreme for direct observation. As we drift further into the cosmic night, we recognize that even the quietest particles can carry stories of unimaginable power. Soft arrivals from violent origins, messengers crossing the darkness, still arriving. As we follow these quiet messengers back to their origins, our path leads naturally toward one of the most mysterious objects in the universe: black holes. They are often imagined as cosmic vacuums, endlessly devouring everything nearby, but the truth is subtler and far more fascinating. A black hole forms when an enormous amount of mass is compressed into a region so small that gravity becomes overwhelming. The escape velocity exceeds the speed of light. Once something crosses a boundary called the event horizon, it cannot return. Yet black holes are not empty voids. They are regions where space-time itself curves inward beyond ordinary limits. Near a black hole, gravity does not simply pull, it reshapes reality. Time slows, light bends. Paths that would be straight elsewhere become arcs around an invisible well. If you could observe from a safe distance, you would see stars behind the black hole distorted into rings and arcs, a phenomenon known as gravitational lensing. Matter falling toward a black hole rarely vanishes quietly. Before crossing the event horizon, it often forms a bright accretion disk. Gas spirals inward, heating to extraordinary temperatures, emitting X-rays and visible light. In some cases, powerful jets erupt from the poles, blasting streams of particles far into space. At the center of nearly every large galaxy lies a supermassive black hole. Even our own galaxy hosts one, quietly influencing the motion of stars around it. Most of the time, these central black holes remain relatively calm, but when they actively consume surrounding material, they can outshine entire galaxies. What happens inside a black hole remains uncertain. General relativity predicts a singularity, a point of infinite density where known laws break down. Yet quantum physics suggests that infinities signal incomplete understanding. A deeper theory, uniting gravity and quantum mechanics, may eventually describe what truly occurs. There is also a surprising insight from quantum theory. Black holes are not entirely black. Over immense timescales, they emit faint radiation, slowly losing mass. This process, known as Hawking radiation, implies that black holes can eventually evaporate, though over periods far longer than the current age of the universe. Black holes embody extremes. They are simple in description, defined only by mass, spin, and charge, yet complex in behavior. They test our theories at their limits. As we drift near their invisible boundaries, we feel no sudden violence, only curvature, only the quiet bending of space and time. In the depths of gravity's hold, light circles, time slows, and the universe reveals that even its darkest objects are woven from the same elegant laws that guide the stars.
As we move gently away from the intense gravity of black holes, our attention shifts to something far more subtle, something so faint that it fills the universe almost unnoticed. Long before stars and galaxies formed, the universe was a glowing sea of hot plasma. Light could not travel freely. Photons scattered constantly off charged particles, trapped in a dense, opaque fog. But as the universe expanded and cooled, a remarkable transition occurred. Protons and electrons combined to form neutral atoms. Suddenly, light was free to move unimpeded. That ancient light is still with us. It has been traveling for nearly the entire age of the universe, stretched by cosmic expansion into microwave wavelengths. Today, it appears as a faint, nearly uniform glow, detectable in every direction. This is the cosmic microwave background. Though it seems smooth, careful measurement reveals tiny temperature variations, differences of only a few millionths of a degree. These slight fluctuations are not random. They represent the earliest seeds of structure. Regions that were slightly denser than average eventually attracted more matter through gravity, growing into galaxies and clusters over billions of years. In a sense, the entire large-scale architecture of the cosmos is encoded in that faint radiation. By mapping these minute variations with exquisite precision, scientists have learned remarkable details. They have estimated the universe's age, measured its overall composition, and confirmed that ordinary matter makes up only a small fraction of the total. Most of the cosmos consists of dark matter and dark energy, components we cannot see directly, but whose effects are measurable. The cosmic microwave background also carries subtle patterns of polarization, faint signatures that may hint at events in the earliest moments after expansion began. Some researchers search for traces of primordial gravitational waves, ripples in spacetime itself, that could have been generated during an extremely rapid expansion phase known as inflation.
The background radiation is not dramatic. It does not blaze brightly across the sky. It hums softly, detectable only with sensitive instruments. Yet it is one of the most powerful sources of information about the universe's infancy. As we rest beneath the night sky, unaware of this invisible glow, it surrounds us completely. It passes through walls, through planets, through space itself. A quiet echo from a time when the cosmos was young and luminous. In its faint warmth lies a record of beginnings. The universe expanded. Light was released, and that ancient glow still drifts across the vastness, carrying whispers from nearly 14 billion years ago.
As the ancient glow of the cosmic microwave background fades gently into the distance of our thoughts, another invisible presence begins to emerge, one that does not shine, does not emit light, yet quietly shapes the structure of everything we see. Dark matter. Unlike dark energy, which influences the expansion of space, dark matter gathers. It exerts gravity, it pulls, but it does not interact with light in any detectable way. We cannot see it directly. We infer its presence through motion. When astronomers measure how stars orbit within galaxies, they notice something unusual. The outer stars move faster than expected. Based on visible matter alone, those stars should drift away, escaping the galaxy's pull. Yet they remain bound. Something unseen is adding extra gravity. The same pattern appears on larger scales. Galaxies within clusters move as though more mass is present than telescopes can detect. Even the bending of light around massive objects, gravitational lensing, reveals additional mass lurking invisibly in the background. Dark matter appears to form vast halos around galaxies. These halos extend far beyond the luminous stars and gas. In fact, most of a galaxy's mass may consist of this unseen component. Without it, galaxies as we know them might never have formed. In the early universe, dark matter likely provided the scaffolding upon which ordinary matter accumulated. What is dark matter made of? That question remains unanswered. It is not composed of atoms like the matter we are familiar with. It does not emit or absorb light. Many scientists suspect it may consist of new kinds of particles, perhaps slow-moving and weakly interacting. Experiments deep underground search for rare interactions between dark matter particles and ordinary matter. So far, results have been inconclusive. Other ideas propose modifications to our understanding of gravity itself. Perhaps on very large scales, gravity behaves slightly differently than current theories predict, but most evidence still favors the presence of additional unseen mass. Dark matter is patient. It does not glow or flare. It does not announce itself with dramatic bursts. It reveals itself only through gentle gravitational influence. As we imagine the universe without it, galaxies would look different. Their formation would have unfolded differently. The cosmic web, the vast network of filaments connecting clusters across immense distances, might not exist in its current form. Invisible, yet essential. Silent, yet shaping motion. Dark matter reminds us that much of reality operates beyond direct perception. What we see, the stars, the glowing nebulae, the spiral arms, is only a fraction of the whole. Beneath the luminous surface lies hidden structure, and within that hidden framework, galaxies continue to turn, held together by gravity we cannot see. As dark matter quietly shapes the architecture of galaxies, we begin to see the universe not as a scattered collection of stars, but as a vast, interconnected structure. On the largest scales, galaxies are not distributed randomly. They form an immense pattern known as the cosmic web. Imagine filaments stretching across incomprehensible distances, connecting clusters like strands of silk in an enormous three-dimensional network. Between these filaments lie vast regions of relative emptiness called cosmic voids. These voids can span hundreds of millions of light years, containing very few galaxies at all. This grand structure did not appear instantly. It grew gradually from the tiny fluctuations imprinted in the early universe. Regions that were slightly denser attracted more matter. Over billions of years, gravity amplified these small differences, pulling gas and dark matter into elongated threads and dense nodes. Within those nodes, galaxies gathered in clusters. Some clusters contain thousands of galaxies, bound together by gravity and enveloped in halos of dark matter. Hot gas fills the space between them, glowing faintly in X-rays. The scale of these systems is difficult to fully imagine. Yet, even within this vast network, motion continues. Clusters drift slowly relative to one another. Filaments evolve. Matter flows along these cosmic highways toward denser regions, gradually deepening the web's structure. The cosmic web is not only a map of where matter resides, it is a record of time. By observing distant portions of the web, we see earlier stages of its formation. Light from those remote regions began its journey when the universe was younger, revealing how structure has changed across billions of years. Computer simulations help scientists visualize this growth. By inputting the known laws of physics and initial conditions from the early universe, researchers can recreate the emergence of filamentary patterns strikingly similar to what telescopes observe. These models confirm the central role of dark matter and gravity in sculpting large-scale structure. And yet, much remains to be explored. The exact nature of dark matter influences how the web formed. Small differences in particle properties could subtly alter the distribution of galaxies. Observations continue to refine these models, comparing theory with ever more detailed surveys of the sky. As we drift through this immense network in imagination, we recognize that our own galaxy is simply one node among countless others. We reside within a filament connected gravitationally to neighboring systems across millions of light years. The universe is not chaotic. It is organized on scales far beyond human experience. Threads of gravity stretch through darkness. Clusters glow softly within them. And across this quiet cosmic web, matter continues its patient flow through time. As we drift along the vast filaments of the cosmic web, our thoughts return once more to the question of expansion. We have seen that dark matter gathers and binds, building structure. But there remains that other influence, the one that gently pulls everything apart. Dark energy. Its presence is subtle, yet its effect is immense. While gravity works to draw matter together, dark energy works in the opposite direction, stretching space itself. On small scales, within galaxies, within clusters, gravity dominates. Stars remain bound, planets stay in orbit. But across the largest distances, dark energy gradually takes control. Measurements suggest that about 70% of the universe's total energy content exists in this mysterious form. It does not clump, it does not form structures. Instead, it appears evenly distributed throughout space, influencing expansion uniformly. What might dark energy be? One possibility is that it is an inherent property of empty space. Even in a perfect vacuum,
quantum physics suggests that tiny fluctuations occur constantly. These fluctuations carry energy. If space itself possesses a baseline energy density, that could drive accelerated expansion. In this view, dark energy is not a new substance, but a feature woven into the fabric of reality. Another idea proposes that dark energy may evolve over time. Instead of being constant, it could be associated with a dynamic field permeating the universe. As the cosmos ages, the strength of this field might change, altering the rate of expansion. The future of the universe depends on this behavior. If dark energy remains constant, expansion will continue accelerating. Over trillions of years, distant galaxies will move so far away that their light can no longer reach us. The observable universe would shrink to our local gravitational neighborhood. Beyond that, space would stretch into quiet isolation. In more extreme scenarios, if dark energy were to grow stronger, expansion could eventually overcome even the binding forces within galaxies and atoms. But current observations do not suggest such dramatic outcomes. For now, acceleration appears steady and gentle. The mystery of dark energy is profound, not because it is violent, but because it is pervasive. It influences the destiny of everything while remaining almost undetectable directly. As we imagine the far future, stars will burn out, galaxies will dim, expansion will continue, the universe will grow colder and more diffuse. Yet for now, we exist in a luminous era. Stars shine brightly, galaxies remain visible, structure fills the sky. Dark energy stretches space quietly, gravity gathers matter patiently. Between these two influences, the cosmos evolves, balanced between attraction and separation, unfolding slowly through time.
As expansion continues its quiet work and gravity continues to gather, another layer of mystery rises gently into view. We have spoken of matter, of dark energy. But what if our understanding of gravity itself is incomplete? For more than a century, Einstein's general theory of relativity has described gravity not as a force in the traditional sense, but as the curvature of spacetime. Massive objects bend the geometry around them. Planets follow curved paths not because they are pulled by invisible strings, but because they move along the natural curves shaped by mass. This theory has passed every major test with remarkable precision. It predicts how light bends around stars. It explains the motion of planets. It describes black holes and gravitational waves. And yet, on the largest cosmic scales, questions remain. Some scientists ask whether what we attribute to dark matter and dark energy could partly reflect a deeper modification of gravity. Perhaps under extreme distances or weak accelerations, gravity behaves slightly differently than predicted. Small deviations might accumulate over vast expanses, producing effects that resemble unseen matter or mysterious energy. Several alternative theories attempt to adjust gravity's equations. They introduce new terms or fields that modify behavior without requiring additional unseen substances. These ideas are carefully tested against observations. Any successful theory must reproduce the precise measurements already confirmed within our solar system, while also accounting for galactic and cosmic phenomena. So far, dark matter and dark energy remain the most consistent explanations, but the door remains open. Science advances by questioning its foundations, even when those foundations are strong.
gravitational waves provide another window into this exploration. When massive objects accelerate, such as when black holes merge, they create ripples in spacetime. These waves travel across the universe, stretching and compressing space as they pass. Detecting them confirms relativity's predictions in dynamic, extreme conditions. Each new detection refines our understanding. The waves carry information about mass, spin, and distance. They reveal collisions that occurred billions of years ago. In listening to these ripples, we test gravity in its most intense forms. The deeper we look, the more we realize that gravity is both familiar and mysterious. It shapes apples falling from trees and galaxies spanning millions of light years. It binds atoms in neutron stars and governs the expansion of the universe itself. Perhaps our current equations are complete. Perhaps they are approximations of a deeper truth still hidden. For now, space-time curves gracefully. Mass shapes geometry, and gravity continues its quiet conversation between matter and motion, whispering across the vastness of existence.
As gravity curves space-time and expansion stretches the cosmos, we come to another profound mystery: time itself. We experience time as a steady flow. Seconds become minutes, minutes become years. We remember the past, but not the future. This direction, this sense of forward motion, feels natural and inevitable. Yet when physicists write down the fundamental equations that govern particles and forces, most of them do not prefer a direction. They work equally well forward or backward. So why does time seem to move only one way? The answer may lie in entropy. Entropy is often described as a measure of disorder, but more precisely, it reflects the number of ways a system can be arranged. Systems naturally evolve toward states with more possible arrangements. Ice melts into water because there are more microscopic ways for water molecules to move freely than to remain locked in crystal form. The early universe appears to have begun in a state of extraordinarily low entropy. It was hot and dense, yet remarkably smooth. Over billions of years, entropy has increased. Stars formed, burned, and spread heavier elements. Structures emerged and evolved. This gradual increase gives time its arrow, its direction from lower to higher entropy. But why did the universe begin in such a special, low entropy state? That question remains open. Some theories suggest that cosmic inflation, a rapid expansion in the earliest moments, smoothed out irregularities and set initial conditions. Others explore the possibility that our observable universe is part of a larger multiverse, where many regions exist with varying conditions, and we inhabit one compatible with complexity. Time behaves strangely under gravity as well. Near massive objects, time slows relative to distant observers. This is not a metaphor. It has been measured. Clocks aboard satellites tick slightly faster than clocks on Earth's surface because they experience weaker gravity. Without correcting for this difference, global navigation systems would fail. Black holes amplify this effect dramatically. Near the event horizon, time for an outside observer appears to nearly freeze relative to someone far away. Space and time intertwine in ways that challenge intuition. There is also a quantum perspective.
At the smallest scales, time may not flow smoothly. Some approaches to quantum gravity suggest that space-time itself could be granular, composed of discrete units rather than continuous fabric. If so, our smooth experience of time might emerge from deeper underlying structure. As we reflect quietly, we realize that time is both familiar and mysterious. It shapes our lives, governs motion, and defines change. Yet its origin, its direction, and its ultimate nature remain partially veiled. The universe expands, entropy increases, and time, silent and relentless, carries everything gently forward.
As time carries everything forward, another question slowly rises from the quiet depths of cosmology. What will become of the universe in the distant future? If the current understanding of dark energy remains correct, expansion will continue accelerating. Galaxies beyond our local group will drift farther and farther away. Over unimaginable spans of time, their light will stretch and fade until it can no longer reach us. Future observers, living trillions of years from now, might look into the sky and see only their own galaxy, unaware of the vast cosmic web that once surrounded them. Stars, too, will not shine forever. The most massive stars burn brightly but live briefly, ending in dramatic explosions. Smaller stars, like our Sun, burn more slowly, yet even they will eventually exhaust their nuclear fuel. They will swell into red giants, shed their outer layers, and leave behind compact remnants, white dwarfs glowing faintly as they cool. Given enough time, star formation itself will decline. The supply of cold gas needed to form new stars will diminish. Galaxies will grow quieter. The universe will enter what some call the era of degenerate matter, dominated by stellar remnants and long-lived low-mass stars. Beyond that lies even deeper time. White dwarfs will cool into black dwarfs. Neutron stars may slowly lose energy. Black holes, once thought eternal, will gradually evaporate through Hawking radiation. This process is unimaginably slow, requiring timescales far exceeding the current age of the universe, but eventually, even the largest black holes could fade away. If expansion continues steadily, the cosmos may approach what is known as heat death, a state where matter is spread thinly, energy differences are minimal, and little organized activity remains. Not a fiery end, but a gradual fading into uniformity. There are other possibilities. If dark energy behaves differently than currently measured, the future could unfold in unexpected ways. But current observations suggest a slow, cooling expansion rather than sudden catastrophe. This vision of the distant future is not meant to unsettle. It unfolds across timescales so vast that human history occupies only a fleeting instant by comparison. For billions and billions of years, stars will continue to shine. Galaxies will continue to evolve. We exist in a luminous era, when structure is rich and the sky is bright. The future may stretch toward quiet simplicity, but the present remains vibrant. As we rest beneath the night sky, aware of both beginnings and endings, we recognize something peaceful. The universe is dynamic. It changes, it evolves. And in its immense timeline, we are part of a brief, glowing chapter, carried gently forward through expanding space and unfolding time. As awareness awakens within the universe, another question gently follows. Are we alone in this vast expanse, or is consciousness scattered like distant stars across the cosmic web? For centuries, this question lived mostly in philosophy and imagination. Today, it belongs equally
spectrographs examine the thin layers of exoplanet atmospheres, searching for chemical signatures that might hint at life. Oxygen, methane, water vapor. On Earth, these gases are closely linked to biological activity. If found together in unusual balance elsewhere, they could suggest processes not easily explained by geology alone. But interpretation requires caution. Planets are complex systems. Chemistry can mimic biology, and biology can be subtle. The search extends beyond atmospheres. Radio telescopes listen for artificial patterns, signals too narrow, too structured to be natural. For decades, silence has answered our listening, yet silence is not proof of absence. The galaxy is vast. Signals weaken with distance. Civilizations may be rare, brief, or communicating in ways we do not yet recognize. There is also the possibility that life may not resemble what we expect. On Earth, life thrives in extreme environments, deep beneath oceans, within acidic pools, in frozen deserts. These discoveries have broadened our view of habitability. Perhaps life elsewhere adapts to conditions we would once have considered impossible. Even if simple microbial life is common, technological civilizations may be far rarer. The development of intelligence capable of reshaping its environment may depend on delicate evolutionary pathways. Small changes in climate, asteroid impacts, or biological competition can redirect history. Yet the universe contains hundreds of billions of galaxies. Each galaxy holds hundreds of billions of stars. Even rare events, when multiplied by such numbers, may occur more than once. The question of companionship in the cosmos remains open. And there is a quiet beauty in that openness. Whether life is abundant or scarce, the search itself connects us more deeply to the universe. It encourages patience. It invites humility. It reminds us that our planet, though small, is part of something vast and shared. As we rest beneath the night sky, we can hold two truths gently at once. We may be alone in our immediate surroundings, or we may be one voice among many, separated by unimaginable distances. The stars continue to shine. Signals, natural and perhaps artificial, continue to travel. And somewhere within this immense expanse, the possibility of other wondering minds quietly endures.
As we consider the possibility of other minds beneath distant skies, we return gently to our own vantage point. Our understanding of the universe has grown through careful observation, patient measurement, and instruments that extend our senses far beyond their natural limits. Telescopes do not simply magnify light, they gather it. Faint photons that have traveled billions of years are collected by mirrors and lenses, concentrated into signals that reveal distant galaxies, newborn stars, and subtle distortions in spacetime. Each improvement in sensitivity opens a deeper layer of the cosmos. Radio arrays spread across deserts combine signals from widely separated antennas, effectively creating virtual telescopes as large as continents. Space-based observatories avoid atmospheric interference, capturing wavelengths blocked from the ground. Infrared detectors peer through dust clouds, revealing star formation hidden from visible light. With these tools, we map the distribution of galaxies, measure their expansion rate of the universe, and trace the faint glow of ancient radiation. We detect exoplanets by the slight dimming of starlight. We observe black holes not by seeing them directly, but by imaging their shadows they cast against luminous backgrounds. Even gravitational
measured by instruments capable of detecting changes smaller than the width of a proton. These detectors stretch and contract as waves pass through Earth, confirming events that occurred billions of years ago. Each technological advance refines our questions. With greater clarity, mysteries sharpen rather than disappear. The more precisely we measure expansion, the more carefully we examine discrepancies. The more planets we discover, the more diverse they appear. And yet, despite all this sophistication, the universe retains its vastness. For every answer gained, new layers of complexity emerge. The horizon shifts outward. There is something profoundly peaceful about this process. Science does not rush to conclusions. It proceeds step by step, correcting itself when necessary. It embraces uncertainty not as weakness, but as invitation. As we drift quietly through these reflections, we recognize that our species occupies a brief moment in cosmic time. The instruments we build are extensions of curiosity. They allow the universe to reveal itself gradually through data and light. We are not separate from the cosmos we study. We are participants, observers shaped by stardust, constructing devices from atoms forged in ancient suns, using them to measure galaxies billions of light years away. The universe expands. Our knowledge expands with it, and through careful observation, we continue to trace the gentle contours of a reality far larger than any single lifetime.
As our instruments extend our sight deeper into space, another realization slowly settles in. The universe we observe is not only vast in distance, it is vast in possibility. Every discovery reshapes our sense of scale. There was a time when our galaxy was thought to be the entire universe. Then, better telescopes revealed that the faint spiral shapes in the sky were not clouds within our system, but entire galaxies of their own. Billions of stars, each potentially hosting planets, stretching far beyond the boundaries we once imagined. Today, we know that the observable universe contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Around many of those stars orbit planets, worlds of rock, gas, ice, and perhaps oceans. The sheer number challenges intuition. Our minds are not built to hold such scale easily. And yet, the laws governing all of it are remarkably simple at their core. Gravity pulls, light travels at a constant speed, atoms bond according to consistent rules. From these steady principles emerges extraordinary complexity. We often think of the universe as distant, something above us, beyond us. But in truth, we exist within it, woven into its ongoing evolution. The oxygen we breathe was forged in stellar interiors. The elements in our bodies were scattered by ancient explosions. Even the photons warming your skin began their journey in the core of the sun minutes ago. This perspective invites a quiet shift in awareness. The universe is not only something to observe, it is something we are part of. As galaxies drift apart under accelerating expansion, as stars are born and fade, as black holes merge and release ripples through spacetime, we remain connected to those processes through shared physical laws. There may always be mysteries beyond our reach, regions of space we cannot see, epochs of time we cannot observe directly, questions about origins and ultimate fate that stretch beyond current understanding. But within this moment, this luminous era of cosmic history, we have access to extraordinary knowledge.
We can trace the universe back to its earliest light. We can map the large-scale structure of galaxies. We can detect particles that pass invisibly through Earth. That capacity is rare, perhaps fragile, but deeply meaningful. As we drift gently toward the close of this journey, the vastness no longer feels overwhelming. It feels expansive in a different way, open, patient, unfolding. The universe continues. Galaxies turn, light travels, and within this immense and evolving reality, awareness quietly persists, looking outward into the dark and finding wonder.
As our journey gently approaches its quiet close, we return to where we began, not to a specific place in space, but to a feeling. The universe is vast. It expands, evolves, and unfolds across distances and timescales almost beyond comprehension. Yet within that immensity, there is a steady rhythm. Galaxies drift apart under the influence of dark energy. Dark matter forms invisible scaffolding for structure. Stars ignite from collapsing clouds, shine for millions or billions of years, then fade into remnants. Black holes curve spacetime. Neutron stars compress matter to extremes, and neutrinos slip silently through it all. On the largest scales, the cosmic web stretches like an intricate lattice. On the smallest scales, quantum fluctuations ripple through empty space. Between these extremes lies everything we experience: planets, oceans, atmospheres, and thought. What makes the universe remarkable is not only its size, but its coherence. The same physical laws operate everywhere we look. The light from distant galaxies follows the same principles as the light from a candle. Gravity binds clusters of galaxies and keeps your feet grounded to Earth. There is elegance in that consistency. And still, mystery remains. We do not yet fully understand dark energy. We continue searching for the nature of dark matter. We explore the origins of time, the imbalance of matter and antimatter, and the possibility of life beyond our planet. Each question leads to deeper inquiry, not frustration. The unknown is not empty, it is fertile. As we reflect on everything we have drifted through, the expansion of space, the listening for signals, the birth of galaxies, the storms of distant planets, the hidden oceans of icy moons, we recognize a pattern. The universe is dynamic, it is layered, it is filled with processes both violent and serene. And through it all, there is continuity. Light travels patiently across billions of years. Particles carry messages from extreme environments. Structures evolve gradually under gravity's guidance. Time moves forward, increasing entropy, shaping change. Now, in this quiet moment beneath the night sky, the vastness feels less distant. It is not pressing in on us. It is holding us gently within its unfolding story. You are made of the same atoms that shine in stars. You breathe the products of ancient stellar furnaces. You exist in a brief, luminous chapter of cosmic history. The universe will continue long after this moment passes. It will expand, it will cool, it will change. But right now, it is bright with galaxies, alive with motion, rich with mystery. So let your thoughts soften. Let the scale comfort you. The cosmos stretches outward endlessly, and you are peacefully within it.